Now we're going to solve a problem that involves equilibrium, but we have forces and torques that are not perpendicular to our line that we can draw from the pivot point to where that force is being applied. Okay, so here's a really great example of this. So we have a uniform horizontal beam right here, which is 5 meters long, and it weighs 300 newtons. Okay, this is the weight of my beam. And it's attached here to the wall by a pin connection that allows this beam to rotate. Okay, if we snipped this is a cable here. If we snipped that cable, then the beam is going to fall this way. Okay, but we have this end of the beam supported by a cable that makes an angle of 53 degrees from the horizontal. Okay, and one more thing. We've got a person right here with a weight of 600 newtons, and they are sitting at a distance of 1.5 meters from the wall. We have to find the magnitude of the tension in this cable and the force exerted by the wall on the beam. Okay, so the only reason why this beam here can be in equilibrium is because there's a force pulling it up here, and there's a force from the wall kind of off in this direction too that's keeping this whole thing in equilibrium from falling down. Okay, so we have to figure out, we're calling R here the force that the wall is exerting on the beam, and T is that tension force in the cable here. Okay, so we have to find both of those. And in order to do that, we're going to have to use both of our conditions for static equilibrium. And that's that the sum of the forces have to equal 0 and the sum of our torques have to equal 0. So let's let's actually draw the free body diagram here. Okay, so we've got the tension force from the cable off in this direction. Okay, so that here is this whole bit right here. That's my tension force, okay, T. And then we've got the weight from my person right here where they're standing, pointing downward. So this is the weight of my human. And then we have the weight of the board, which is located at half its length, assuming our board is uniform. And that's going to be right here at half of 5 meters. So 2.5 meters, and so that's the weight of the board here. Okay, so that's my free body diagram. We do also have, not quite, it was almost a free body diagram. We've got the force that the wall is exerting here on my beam. Okay, that force is going to be pointing off in kind of this direction, we'll find eventually, okay? But it has a component, so, well, maybe I'll just draw it. I know that it looks like this, but it's going to have a component that we're going to call Ry. Now it's going to have a component this way, Rx. Okay, so the wall is exerting a force this way on the beam, and it's exerting a force this way on the beam. Okay, and so then we can put those together using our Pythagorean theorem in order to get that total force, the magnitude of that total force here. Okay, now we have to figure out what these two are, and in order to do that, we have to use our conditions for equilibrium. So let's use first our condition that the sum of all the torques has to equal 0 and see how that helps us. All right, so we've got our sum of our torques must equal 0. And let's see what torques we have. We have the torque coming here from the force that the wall is exerting on my beam, which I'm going to call T sub R. We've got the torque from the weight of the person, torque human, plus torque from the weight of the board, plus the torque from my cable here. We'll call it sub T. That all has to equal 0. Okay, now I just put it in here. I didn't take into account like the positive and negative signs that go onto the torques. So let's think about that. If we're going to let everything rotate or pivot around this beam point right here where it's connected to the wall. We said that in the problem there was a connection, like a little pin that's put in here so that the beam connects to the wall. Okay, so that's going to be our pivot point. Now, the force that the wall is exerting on the beam is sitting right at the pivot point. Okay, so that means that its torque is 0. Anytime you have a force applied right at a pivot point, there is no torque from that force. So that is 0. Okay, the torque from our person. So if we cut this cable the torque from the person is going to move this beam in this direction clockwise. So that's a negative torque, okay? Same thing if we cut this right here, this cable, the torque from the beam is a clockwise torque, so that's a negative torque. And then if we come over here and we just tug and tug and tug even more on this cable right here, we're going to pull the beam upward and move it in this direction. So that's a counterclockwise torque opposite the direction that the clock runs. So that's a positive torque. So we're actually going to have minus the torque from the human's weight, minus the torque from the weight of the beam, plus the torque from this cable here has to equal 0. Okay, so we've got, I'm going to call this minus RH. RH is the distance that human's weight is away from the end of our board here, times the weight of the human, minus RB, that's where we can say the center of gravity is of my beam away from the pivot point, so that's half the length of my board, times the weight of the board, plus we've got the torque here from my cable. So what is that torque? So that's going to be the distance that torque is applied from the end of my pivot point here. So I'm going to call that, well, in this case, that's the total length here. So I will just call that, well, I'll still call it R sub t. And then we've got my force T here, the tension force sine theta. So we're actually going to use our torque is equal to RF sine theta, okay? And so this angle theta here, that's going to be our 53 degrees right here, okay? That's our 53 degrees. So, and that all has to equal 0. So then, if I solve this equation for t, because I know everything else here, if I solve this equation for t, I'm going to see that I'm going to have move all of these two terms that are negative to the other side of my equal sign. I'm going to have RT times T sine theta equals RH WH plus RB WB. And then I need to solve this for T. So I'm going to divide both sides by RT sine theta. So T is equal to RH WH plus RB WB divided by RT sine theta. Ooh, I keep on drawing it. It's a perpendicular sign here. Divided by RT sine theta. Okay, so let's fill in this. Remember that RH is the distance that human is from the pivot. And so that's going to be 1.5 meters times the weight of our human, which is 600 newtons, plus the distance that our center of gravity of our board or our beam is away from the pivot, which is going to be centered at half its length. So that's going to be, the whole length of the board is, or beam is 5 meters, so half the length is going to be 2.5 meters times the weight of my board, 300 newtons. All of that divided by, okay, where this tension force is being applied here, that's at the whole end of the length of my board. So that's going to be 5 meters times sine of this angle right here, 53 degrees. Okay, so then we find that the tension on my cable is equal to 413 newtons once we plug in all of those values right there. Okay, the tension is 413 newtons. So we already found that part by using the sum of our torques. Now to get the force that the wall exerts on the beam, we have to use Newton's second law. We're going to have to use Newton's second law in both the x and the y direction, of course, because this tension has an x and a y component. So let's say we've got the sum of our forces in the x direction has to equal 0, and we've got the sum of our forces in the y direction that also has to equal 0. So let's first work on the sum of our forces in the x direction. Okay, so we're going to have the x component from this force on the wall, and that's going to be pointing off in this direction. Okay, the wall is exerting a force in this direction on my beam. So I'm going to say that's Rx, a positive x direction, and I'm just going to call it Rx here, okay? And then, so I've got Rx, what's my other force in the x direction? Oh, I've got the component of my tension force in the x direction, but that tension force is pointing off in this direction here. That's in the minus x direction. So we've got minus, let's see, we've got to figure out what is the x component of this tension force. Okay, so we've got our angle theta here. T is the hypotenuse of this little triangle here. So the x component is going to be this side down here, which is adjacent to our angle theta. So this x component for my tension is going to be T cosine theta. Okay, so we've got the x component from the force of the wall on the beam minus the x component of the tension force at the end of the beam, which is minus T cosine theta, and that has to equal 0. So we find that the x component of the force that the wall is exerting on the beam is just equal to T cosine theta. So if I plug in the tension that we just found, 413 newtons, times cosine of my angle 53 degrees, then the x component that the force that the wall is exerting on the beam is equal to 249 newtons. Okay? And now we do the same thing for the forces in the y direction. This one is, though, a little bit more complicated. So for the forces in the y direction, we have more than 2 forces. We've got 4 forces. Okay, this is all equal 0. So we've got the y component of the force that the wall is exerting on the beam, so I'll just call that Ry. And then we've got the y component of our tension force upward as well, okay? So if the x component of my tension force was T cosine theta, then the y component of my tension force is T sine theta, okay? So then I've got Ry plus T sine theta, and then minus the weight of my human and the weight of the beam. Those are all pointing down. So then we've got minus the weight of the human minus the weight of the beam. That all has to equal 0. So then the y component of the force that the wall exerts on the beam is equal to the weight of the human plus the weight of the board minus T sine theta. Okay, so the weight of the human was 600 newtons. The weight of the beam was 300 newtons. And we've got to say minus our tension force was 413 newtons. Sine of my angle here, 53 degrees. Okay, so then the y component of this force that the wall exerts on the beam is equal to 570 newtons. Okay, so we've got the x component of that force, the y component of that force. So the x component of that force that the wall exerts on the beam is 249 newtons. The y component of that force is 570 newtons. So our vector here for the force that the wall, total force that the wall exerts on the beam looks like this. So it's pointing off in this direction. And we've got 2 legs of a right angle triangle here. We use Pythagorean theorem to find the magnitude of this force, and that's going to equal to the square root of Rx squared plus Ry squared. And so this is our x component, 249 newtons. This is our y component, the 570 newtons. And so that tells us that the total force, or the magnitude of the force that the wall exerts on the beam is 622 newtons, okay? And we found the tension that must be in this cable in order for everything to be in equilibrium. We found that by using our other condition for equilibrium, that the sum of the torques has to equal 0. So why do we care about these types of problems? Well, these are things that engineers are doing all of the time. Engineers are working on these equilibrium problems in order to build bridges, to hang signs, to build buildings. They need to figure out what do we have to do, what forces do we need in order for everything to be in equilibrium.